Okay, in this video, we're going to be doing assignment 11, part 2 from my Calc CD multivariable class. We're going to be verifying that our vector field f is the gradient of our potential function, and then we'll evaluate the line integral of f over the given path. So let's take a look. Number 3, our vector field is 3, 6y. Our potential function is 3x plus 3y squared, and then our path, r of t, is going to be t, t over 2. And we are going from 1 to 4 for t values. So the first step is we got to show that the gradient of this is actually f, so we're going to find partial x and partial y. So partial x is just 3, and then partial y is just going to be 6y. And so, in fact, we did find that f is the gradient of our potential function. So now what we need to do is figure out where we're starting and where we're stopping. So we're starting at r of 1, and r of 1 is going to be 1, 2. And then we're stopping at r of 4, and r of 4 is going to be 4, 1/2. So now what we'll do, instead of directly calculating this line integral, what we'll do is we'll use the fundamental theorem. So it's going to be f of where we stop, so f of 4, 1/2, minus f of where we start, which is 1, 2. And we sub into our function f, and we get 12 plus 3/4, and then minus 3 plus 12, and overall that gives us negative 9/4. All right, let's look at the next one. So f, our vector field, is cosine y, negative x sine y. Our potential function is x cosine y. Our path is cosine, sine, and we're going from 0 to pi. We got to confirm that our vector field is in fact the gradient of our potential function, so we'll find partial x, partial y. Partial x, if you do it for this, is just going to be cosine of y. Partial y is going to be x times the derivative of cosine y. So it's going to be negative sine of y times x, or negative x sine of y. Look at what we were given. It is the case that our vector field is the gradient of our potential function. So now we can use the fundamental theorem of line integrals. And so let's see if we can do that. So it's going to be r of 0, where we started, is just 1, 0. R of pi, where we're ending, is negative 1, 0. So our line integral will be f of where we end, which is negative 1, 0, minus f of where we started, which is 1, 0. Now we go up to f and we plug in. So we get negative cosine of 0 minus 1 times cosine of 0, which is going to give us negative 1 minus 1, which is negative 2. All right, let's take a look at the next one. So we've got our vector field. I'm not going to read it. We got our potential function, which is x, y, e to the z. We have our path, which is t squared, t cubed, t minus 1, and we're going from 1 to 2. Let's confirm that our vector field is in fact the gradient of our potential function, which is x, y, e to the z. So we need partial x, which is just going to be y e to the z. We need partial y, which is just going to be x e to the z. And then we need partial z, which is actually x, y, e to the z. Now compare that to the vector field we were given, and you can see that it is in fact the gradient of our potential function. So we will find where we start, we'll find where we stop, and we'll use the fundamental theorem. So we're starting at r of 1. So we're taking 1 and plugging it into r. That gives us 1, 1, and then 1 minus 1 is 0. Then we're going to take 2 and plug it in, and we will get 2 squared, 2 cubed, 2 minus 1, so 4, 8, 1. And then using the fundamental theorem, our line integral is going to be f of where we stopped minus f of where we started, which is almost exactly the same as the normal fundamental theorem that you're familiar with from like Calc 1, Calc AB, way back when you took that. So if we plug 4, 8, 1 into f, we get 4 times 8 times e to the first, so 32e. And then if we plug 1, 1, 0 in, we get 1 times e to the 0, so it's going to be minus 1. And that's as good as that's going to get. All right, we're going to do one more in this one. So f is z over x, 1, natural log of x. That's our vector field. Our potential function is y plus z natural log of x. Our path is going to be the circle x minus 4 squared plus y squared equals 1, and we're going clockwise. So kind of already, if you think about this, if you're going along a circle, it doesn't really matter where you start and stop. You're going to start and stop at the same point. We're definitely getting 0 here. We kind of don't need to do it. But first, we need to make sure that our vector field is actually the gradient of our potential function, because otherwise, all bets are off. So we need the gradient of this. So partial x for this is going to be z times 1 over x, because the derivative of y is just 0 if x is our variable. Partial y is just 1 because there is no y in the z natural log of x term. And then partial z is just going to be the natural log of x because the derivative of y will be 0 and the derivative of z will be 1. So we just get 1 times natural log of x. So we get this. Look at what we were given. That is, in fact, so all of those are the gradient. So f is the gradient of our potential function. Now, let's think about what's happening. Our path looks like this. We're not told where to start and where to stop, so it doesn't really matter. So I'm just going to start at the right edge of this thing, right? Like the farthest right point, like basically treat it like the unit circle. So I'm starting at 5, 0, and I'm also ending at 5, 0, which means when I go to use the fundamental theorem, even if you don't think about it and you just kind of do it, we're definitely going to get 0. And again, if you don't think about it and you just plug in where you end minus where you start without actually having to sub anything in, you can see that you're definitely you're going to get 0 for this thing. All right, I'm going to end this one here. I'm going to be back in the next video to do the rest of this. Hope this was helpful, and good luck.